So, continuing our lectures on electronic devices. So, we will first start with a problem where the mobility of an electron has been said to be 300 centimeters square per volt second. The recombination time of the electron is given as 90 nanoseconds, and the temperature is room temperature 300 Kelvin. So we need to find out the minority carrier diffusion length. That is LE. So LE is nothing but root over dE into tau E, where d is the diffusion coefficient. So from Einstein's relation, dE is given as kT mu E divided by E, and if we put all the values here, it turns out to be equal to 7.75 centimeters square per second, and we put the value in LE, and LE turns out to be equal to 8.4 micrometers. So here this relationship should be considered, and this relationship is it important. The next problem is for a p-n junction which is forward biased. If the P is the positive terminal, of the external power source, and N the negative terminal of the external power source, then it's considered to be reverse biased. It is considered to be a forward bias. And if it is the opposite, that means if the P side is connected to the negative terminal and the N side is connected to the positive terminal, then it is the reverse bias. So again, if we consider a p-n junction in forward biased condition, the current due to lowering of the barrier for the injection, it leads to current. The current flows in it. It is due to lowering of the barrier for the injection. And the current due to injection of the minority carriers. There is a current due to injection of the minority carriers. So these are the two types of current flowing through one current is due to lowering of the barrier, while other current is through lowering injection of the magnetic current passing through a p-n junction. Now, suppose we have a germanium P plus N diode. P plus N stands for the P side is heavily doped, and it is at 300 Kelvin, and we have the acceptor concentration is 10 to the power 18 per centimeter cube. We have the donor concentration as equal to 10 to the power 16 per centimeter cube. The diffusion coefficient associated with electron is 49 centimeter square per volt second, whereas with the DE is, on the other hand, with electron is figure of the holes H. For the holes it is 49 centimeter square per volt second, whereas for the electron it is 100 centimeter square per second. Should be volt second. The lifetime of the hole is equal to the lifetime of the electron recombination time, and it is 5 microsecond, and the intrinsic carrier concentration is 2.4 into 10 to the power 13 per centimeter cube, and the area, cross-section area, is 10 to the power minus 2 per centimeter square. So we need to find out the reverse saturation current density. Sure, the JSO. So JSO is given as, it is equal to ENI square into, there are two terms. First term is DH divided by LHND plus DE divided by LENA, where we know that LE is equal to DE tau E, and Ln is equal to Dn tau n. So if we put all the values, the JSO comes up to equal to 2.9 into 10 to the power 5 ampere per centimeter square. This is the reverse saturation current density. So if somebody tells you to find out the diode current density, considering the same conditions, so J is simply JSO into exponential EV by KT minus 1, and we have been given that there is a forward bias which takes place at 0.3 volts. So only thing unknown is the voltage here, everything is known. So we get a value around 3179.6 ampere, nanoampere per centimeter square. Next topic, that is when we will say that the PN junction has broken down. JPN breakdown is actually the sudden exponential increase in reverse bias current. So it corresponds to sudden exponential increase in reverse bias current, which is beyond a particular external voltage, which is beyond a particular external voltage. It is called the breakdown voltage. So if we assume that the in a PN junction the breakdown has not yet happened, to assume the breakdown has not yet happened. So the current that flows through it is called the reverse saturation current, JSO. And this is a current which is independent of the reverse bias voltage. So this is a current or current density which is independent of reverse bias voltage. Therefore, we don't have an expression of voltage as we have solved it. There is no expression of voltage here. Okay, so it's independent of the reverse bias voltage. And the current is generated by a drift of thermally generated carriers. So JSO or ISO, it is generated by the drift of thermally generated carriers in the depletion region. Now the electron and holes, they are dynamically generated in the depletion region. And they get accelerated towards the N and the P side due to applied voltage. And this leads to a small reverse saturation current, also called the drift current. So it leads to your JSO, and it's also called the drift current. And as we have previously seen, the expression of the drift current JSO is nothing but is equal to ENI square into, there are two expressions, DH divided by LH tau H plus DE divided by LE tau E. And so we can see that the reverse saturation current is independent of reverse bias voltage. So again, we can clearly see that the reverse saturation current is independent of the reverse bias voltage.